Hello and welcome to my presentation on heterogeneous CPU and iGPU processing for efficient epistasis detection. My name is Rafael Campos from INESC ID, and let's get this started. So this work is based on the notion of single nucleotide polymorphisms, or SNPs or SNPs, which are structures that are part of the human genome. And by looking at a pair of chromosomes in the same location, if we examine the gene and it contains differences in a single nucleotide, and this change is present in a significant part of the population, we call this SNP. And these SNPs, different SNPs, can interact with each other to cause a phenotypic trait. Several diseases have been shown to rely on this process, such as Crohn's disease or Alzheimer's. So it has important implications for human health to explore, detect which SNPs interact to cause which phenotypic traits. This process of epistasis has a order of K, which indicates the amount of SNPs interacting, and exhaustive detection of epistasis is when in a data set all possible combinations of SNPs are examined or evaluated for epistasis. These methods are very accurate, although they are demanding computationally. And it is of our notion that using heterogeneous CPU and integrated GPU systems can provide an alternative to the more traditional CPUs and discrete GPUs used for this end. The objectives of this work are thus to develop a framework for single and multi-objective exhaustive search for epistasis and these heterogeneous CPU and iGPU systems. We will adapt an existing algorithm and optimize it for this architecture. Then we will experimentally test this framework in different scenarios, both using one device or more than one device simultaneously. And hopefully we will provide some insight into the trade-offs of using this architecture for performance, but also power consumption and energy efficiency. Here's an overview of the contents of this presentation, and we will start by the problem formulation. So the case control datasets provided contain samples of several SNPs, number M, and also a phenotype value for a number of samples or patients. Each SNP value will be 0, 1, or 2 depending on the alleles that form it being dominant or recessive. The phenotype value will be 0 for control or 1 for case. So when doing exhaustive search, every single combination of different SNPs must be evaluated. Therefore, the search space will grow according to this formula, where M is the number of SNPs and K is the interaction order or epistasis order. For each combination of SNPs, objective functions are used to indicate the likelihood of epistasis happening. These objective functions are based on biological criteria, and two of the most widely used objective functions are the K2 score and mutual entropy, which will be used in this work both for single objective optimization, where only one function is being optimized for, and multi-objective, with the two functions being used. Let's now look at an overview of the algorithm being used for epistasis detection. This algorithm consists on a series of 4 steps identified here. The first step consists on generating a combination of K SNPs to be evaluated. The SNPs are represented in the dataset in a binary representation, where each SNP has 3 binary arrays indicating the values for either 0, 1, or 2. And in this case, we have K equals 2, therefore 2 SNPs in each combination, in this case X and Y. These SNPs will be evaluated by going through all n samples and looking at the genotype values for each SNP and also the phenotype value for each sample. And using these SNPs and the phenotype and a series of logical operations and also population count operations, we can fill a frequency table, which will be used as a support for the computations involving the objective functions. The objective functions or objective function are use this frequency table to obtain a numeric score for each combination, which will be used to evaluate the combination either in single objective optimization, where the minimum of each objective function is used, or multi-objective, where all the solutions must fit inside the Pareto front to minimize both the objective functions being used. And implementing this algorithm in the heterogeneous architecture being used requires knowledge not only of each device in the architecture, but also the common memory subsystem. This architecture consists on CPU cores that have private caches, level 1 and level 2, and also an integrated GPU, which has execution units that are clustered in subslices and have access a common L3 data cache. Both this L3 data cache and the caches for the CPU cores are connected through a ring interconnect to the last level cache, which is common, and therefore these devices have a way of sharing memory. Let's now take a look at the heterogeneous framework used for epistasis detection. This framework is divided according to three different devices. First of all is the CPU master, which contains a scheduler, and this scheduler is responsible for going through every possible combination of SNPs to be evaluated and assigning them either to the integrated GPU or the CPU cores. This is done by, for the CPU cores, assigning an initial combination that will be iterated upon, and for the integrated GPU, assigning a vector of combinations that will be received by the iGPU. This CPU master uses adaptive scheduling, measuring the performance in real time of the integrated GPU and the CPU cores, and assigning work accordingly. For the CPU cores, the initial combination is received, and all 4 steps of evaluation are done using SIMD instructions to construct the frequency table, and also for the score calculation and the evaluation are used lookup tables to avoid redundant scores. And each CPU core will keep their local solution or their local Pareto front. As for the integrated GPU, the SIMD instructions used are 128-bit wide, and the same lookup tables are used. The solutions are kept locally also, but only in the case of single objective optimization. As in the case of multi-objective optimization, the Pareto front is merged with the Pareto front of the CPU master. Finally, the CPU master, after all SNP combinations are evaluated, will gather the final solution by reducing the local best solutions for each device or the local Pareto fronts for each device in the case of multi-objective optimization. Now, looking at the experimental results, the experimental setup consisted on a CPU, an 8th generation Intel Core CPU with 6 cores, and an iGPU that contains 24 execution units organized in 3 subslices. 3 different datasets are used for epistasis detection with a differing number of SNPs and samples, and the results are organized also in 2 different epistasis order, k equals 2 and k equals 3. And every result will be presented using 5 different tests with the 3 different datasets and 2 interaction orders, k equals 2 or k equals 3. Represented by these 5 bars. The first result presented will be the population count based algorithm running only in the CPU. And after that, we have the version that is the population count based algorithm running only in the CPU with vectorization enabled. This allows us to compare the effects of vectorization, and looking at these results, we can conclude that using vectorization in the CPU will lead to increased performance. When running only in the iGPU, we obtain these results, and when enabling the scheduler, dividing work between the CPU master thread and only the integrated GPU, not the CPU cores, we obtain these results. Finally, enabling the full framework allows us to obtain the results presented here in CPU plus iGPU. Comparing every result, we are able to conclude that the best result overall is obtained by the full framework, CPU plus iGPU, while the iGPU only obtains the worst results overall. These results are obtained using single optimization with the K-choose score, but when using single objective optimization with the mutual entropy objective function, we obtain very similar results. Looking at the power consumption results, we can see that the lowest power consumption overall is obtained by the integrated GPU, and when comparing the pop count and the pop count VEC versions, we can see that enabling vectorization in the CPU will lead to an increase in power consumption. And when comparing all versions, we can see that the CPU and iGPU version has the worst overall results for power consumption, and these are much higher than, for example, the scheduler version, which has comparable performance. When looking at energy efficiency, we can see that the highest energy efficiency overall is obtained by the scheduler version, and this is due to the high overall performance of this version and its low overall power consumption. Executing in the CPU will yield higher energy efficiency results than the iGPU. Although it has a higher power consumption, it also has higher performance. And when executing in the CPU or the CPU plus iGPU scenario, we have better efficiency than the iGPU only version, and this is due also to this higher performance despite the high power consumption. When looking at the multi-objective results, using only the scheduler and the CPU plus iGPU scenario, we can derive similar conclusions where the best overall performance is obtained by the CPU plus iGPU. However, the scheduler version will have a lower power consumption and higher energy efficiency relatively. And now we reach the conclusions of this work. And we can conclude that exhaustive search methods provide high accuracy, but they have a performance impact and also an energy efficiency impact. But it is of our belief that the heterogeneous framework that is proposed in this work can lead to higher efficiency for this epistasis detection methods using heterogeneous architectures consisting on a CPU and an integrated GPU. We have obtained performance gains of up to 5 times relatively to the base CPU version, and energy efficiency gains of up to 6 times compared to the CPU version. Future directions of this work include extending this heterogeneous framework to hybrid architectures consisting of a CPU and FPGA, and also different CPU and iGPU systems, and also exploring the effects of dynamic voltage and frequency scaling. And that is it for this presentation. Thank you very much.